This is the video for Part 2 of Section 3.3, Isomorphisms and Homomorphisms. We'll start with the definition of an isomorphism. A ring R is isomorphic to a ring S, which is denoted R, and then we have an equal sign with a tilde on top, S, provided that there is a function f from R to S such that 1, f is injective, meaning for all R1, R2, and R, if R1 is not equal to R2, then f of R1 is not equal to f of R2. 2, f is surjective. For each S and S, there exists an R and R, such that f of R is equal to S. And 3, f is a ring homomorphism, meaning that it satisfies properties RH1 and RH2, our preservation of addition and preservation of multiplication. The function f is called an isomorphism. For an example, let's let K be the set of 2 by 2 matrices of the form AB minus BA, where A and B range over the real numbers. So the diagonal entries are the same and the off-diagonal entries are negatives of one another. Then K can be shown to be a subring of M2R, so is a ring. And we want to define f from K to the field of complex numbers by f of the matrix AB minus BA is equal to A plus BI for each matrix in K. So f is mapping 2 by 2 matrices into complex numbers. Then f is an isomorphism, and hence K is isomorphic to C, the field of complex numbers. So to show this, we need to show that f is a ring homomorphism and is injective and surjective. So we'll first show that f satisfies RH1 and RH2. So for RH1, preservation of addition, we need to show for all A, B, and K, f of A plus B is equal to f of A plus f of B. So we'll suppose that A is the matrix AB minus BA, and B is the matrix CD minus DC, and that these are arbitrary elements of K. And we need to show f of A plus B is equal to f of A plus f of B. So the left side is f of A plus B, which is f of the sum of those two matrices, and we can go ahead and sum the matrices and we obtain the matrix shown. So with entries A plus C on the diagonal and B plus D and minus B plus D on the off diagonal. And according to the definition of f, this is equal to A plus C plus the quantity B plus D times I. Now the right side is f of A plus f of B. So this will be f of our first matrix plus f of the second matrix. And this will be the complex number A plus BI plus the complex number C plus DI. And the way we add two complex numbers is we add their real parts and imaginary parts, and we obtain A plus C plus the quantity B plus D times I. And so we can see that the two sides are equal, therefore f satisfies RH1. For RH2, preservation of multiplication, we have to show for all A, B, and K, f of A times B is equal to f of A times f of B. So we'll suppose A and B are the same two arbitrary matrices in K, and we need to show f of AB is equal to f of A times f of B. So we'll start with the left side, and this is f of the product of those two matrices. And taking the product, we obtain f of the matrix with entries AC minus BD and then AD plus BC. And f of this matrix will be AC minus BD plus the quantity AD plus BC times I. Now the right side is f of A times f of B. So this is f of our first matrix times f of our second matrix. And f of the first matrix is A plus BI, and f of the second matrix is C plus DI. So now we have the product of two complex numbers. And taking this product, we obtain AC minus BD plus the quantity AD plus BC times I. And we see that the two sides are equal, and therefore f satisfies RH2. So this shows that f is a homomorphism. Now, to show that f is injective, we need to show for all a, b, and k, f of a equals f of b implies a equals b. So we'll suppose that a and b are the same two arbitrary elements of k. We'll suppose the hypothesis f of a equals f of b. We then need to show the conclusion a equals b. So since f of a is equal to the complex number a plus bi, and f of b is the complex number c plus di, then the hypothesis implies a plus bi equals c plus di. And this implies that a is equal to c and b is equal to d. Two complex numbers are equal provided their real parts are equal and their imaginary parts are equal. So then A, which is the matrix AB minus BA, will be equal to the matrix CD minus DC, which is the matrix B. And so this proves the conclusion, and therefore F is injective. To show that F is surjective, we need to show for all complex numbers Z, there exists the matrix A in K such that F of A is equal to Z. So we'll suppose that Z equal A plus BI is an arbitrary complex number in C. We then need to show there exists the matrix A in K such that F of A equals Z. So we can set this up using the two columns. We need to find a matrix A and then verify that A satisfies our two conditions, namely the domain A belongs to K and our propositional function f of A equals Z. So here I'm just going to choose the matrix A is the matrix AB minus BA. This just follows from the definition of our function. So we've now got our matrix, and since A has the form of matrices in K, then A belongs to K, so our domain condition is satisfied. And then the propositional function holds since f of A is equal to f of the matrix AB minus BA, which is equal to A plus BI, which is equal to Z. So this proves the existential statement, so therefore F is surjective. And this shows that F is an isomorphism. Thus, K is isomorphic to C. So this says that this ring of 2 by 2 matrices is isomorphic to the field of complex numbers. So you can see that these are very different rings, but they're still isomorphic to one another, meaning that they're essentially the same ring, just using different notation. For another example, we want to show that the rings Z5 and Z6 are not isomorphic. So note that for finite sets A and B, if there exists a bijection F from A to B, then A and B must have the same number of elements. Since an isomorphism is a bijection and Z5 and Z6 have different numbers of elements, then Z5 and Z6 cannot be isomorphic. Suppose R and S are rings. Now, according to the definition, R is isomorphic to S provided that there exists an isomorphism F from R to S. Since F is an isomorphism, then F is a bijection, which implies the inverse function F inverse from S to R exists and is a bijection as well. Now, it can be shown that the inverse is also a ring homomorphism and hence is an isomorphism. This implies that S will be isomorphic to R. So therefore, the isomorphism relation is symmetric. For all rings R and S, if R is isomorphic to S, then S is isomorphic to R. This allows us to refer to two rings R and S as being isomorphic instead of saying one ring is isomorphic to the other. Next, we want to consider properties of homomorphisms. Now, since a ring homomorphism preserves the ring addition and multiplication, then it will also preserve any arithmetic properties of the ring. And our theorem 3.10, is going to tell us some of these properties. So let F from R to S be a ring homomorphism. Then first we have F of 0 sub R equals 0 sub S. So this is saying that F maps the additive identity of R into the additive identity for S. So it preserves the additive identities. And then 2, for all elements A in R, F of minus A is equal to minus F of A. So this is saying that f maps the additive inverse of an element into the additive inverse of the image of the element. And 3, for all a, b, and r, f of a minus b is equal to f of a minus f of b. So this is saying that f preserves subtraction. And then if R is a ring with identity, multiplicative identity, and f is surjective, then property 4 tells us that S is a ring with multiplicative identity, and f of 1 sub R is equal to 1 sub S. So f maps the multiplicative identity of R into a multiplicative identity for S. And property 5 says that if U is a unit in R, then f of U is a unit in S, and the multiplicative inverse of f of U will be equal to f of the multiplicative inverse of U. So we'll start the proof by looking at number 1, which is f of 0 sub R equals 0 sub S. And first note that f of 0 sub R is equal to f of 0 sub R plus 0 sub R. That's by axiom R4 in the ring R. And this will be equal to f of 0 sub R plus f of 0 sub R. That's by RH1, the preservation of addition. And also by axiom R4, but in S, f of 0 sub R will be equal to f of 0 sub R plus 0 sub S. So on the one hand, f of 0 sub R is equal to f of 0 sub R plus f of 0 sub R, and on the other, f of 0 sub R is f of 0 sub R plus 0 sub S. So we can set these two expressions equal to one another. And then by theorem 3.4, the cancellation property, this implies that f of 0 sub R is equal to 0 sub S. We can cancel f of 0 sub R from both sides. And so this proves property 1. For property 2, we want to show for all elements a and r, f of minus a is equal to minus f of a. So suppose a is an arbitrary element in R. We need to show f of minus a is equal to minus f of a. Now note that minus f of a, by definition, is the additive inverse of f of a. And to prove this equality, we want to show that f of minus a is the additive inverse of f of a. So to show this, we can show that f of minus a satisfies the property of this additive inverse, namely that f of a plus f of minus a is equal to 0 sub S. So to show that f of minus a is the additive inverse of f of a, we can show that it behaves like the additive inverse of f of a by showing this equality. So starting with the left side, f of a plus f of minus a is equal to f of a plus minus a. This is by RH1, the preservation of addition. And this is equal to f of 0 sub R. That's by axiom R4 in the ring R. And then this is equal to 0 sub S by part 1 of the theorem. So this proves the equality, and therefore f of minus a is equal to minus f of a. So this proves 2. For 3, we want to show that f preserves subtraction. So we'll suppose that a and b are arbitrary elements of R, and we need to show that f of a minus b is equal to f of a minus f of b. So the left side is f of a minus b, which is equal to f of a plus minus b. That's by the definition of a minus b. And this is equal to f of a plus f of minus b. That's by RH1, the preservation of addition. And this is equal to f of a plus minus f of b. That's by part 2 of the theorem. And this is f of a minus f of b. That's by the definition of f of a minus f of b, the definition of subtraction in S. And so therefore f of a minus b is equal to f of a minus f of b, and this proves 3. So for 4, we want to show that if R is a ring with identity and f is surjective, then S is a ring with identity and f of 1 sub R is equal to 1 sub S. So we'll suppose R is a ring with identity 1 sub R and f is surjective. We need to show that S is a ring with identity and f of 1 sub R is equal to 1 sub S. To show this, we need to show that there exists an element 1 sub S in S such that for all S and S, 1 sub s times s is equal to s, and s times 1 sub s is equal to s. So we need to show that there exists a multiplicative identity in S that has the required property to be a multiplicative identity, namely that when you multiply it by any element S in S, we obtain back that same element. Now the theorem tells us what the element 1 sub s should be, namely 1 sub s should be f of 1 sub r. And we know that f of 1 sub r is an element in S, so we just need to verify that f of 1 sub r satisfies the condition that for all S in S, f of 1 sub r times s is equal to s, and s times f of 1 sub r is equal to s. So let's suppose that s is an arbitrary element of S, and we need to show these two equalities, f of 1 sub r times s is equal to s, and s times f of 1 sub r is equal to s. Since f is surjective, then there exists an element r in R such that s is equal to f of r. Then, substituting s is equal to f of r and using property RH2, the preservation of multiplication, we have f of 1 sub r is equal to f of 1 sub r times s is equal to f of 1 sub r times f of r, which is equal to f of 1 sub r times r, that's using property RH2, the preservation of multiplication, and this is equal to f of r, which is equal to s. So this shows that f of 1 sub r times s is equal to s. And similarly, s times f of 1 sub r will be equal to f of r times f of 1 sub r, which is equal to f of r times 1 sub r, which is equal to f of r, which is equal to s. So this proves our two equalities. Therefore, f of 1 sub r is an identity for s, so S is a ring with identity. And this proves 4. And finally, we have property 5. Suppose R is a ring with identity and F is surjective. We want to show that if U is a unit in R, then F of U is a unit in S, and F of U inverse is equal to F of U inverse. So suppose U is a unit in R, and we need to show that F of U is a unit in S, and F of U inverse is equal to F of U inverse. To show that f of u is a unit in S, we need to show that there exists a multiplicative inverse for f of u, that is, an element S in S, such that f of u times S is equal to the multiplicative identity 1 sub s, and S times f of u is equal to 1 sub s as well. So now the theorem statement tells us what the element S should be, namely S should be equal to f of u inverse. Also, by part 4, we know the identity in S is going to be 1 sub s equal to f of 1 sub r. So we need to show that f of u times f of u inverse is equal to 1 sub s, and f of u inverse times f of u is equal to 1 sub s. So using RH2, the preservation of multiplication, for the first equality, we have f of u times f of u inverse is equal to f of u times u inverse, which is equal to f of 1 sub r, which is equal to 1 sub s. And in the other order, we have f of u inverse times f of u is equal to f of u inverse times u, which is equal to f of 1 sub r, which is equal to 1 sub s. So this proves the two equalities, and therefore f of u is a unit with multiplicative inverse. F of u inverse is equal to f of u inverse. And this proves 5. And this completes the proof of the theorem. Next we have a definition. Suppose f from R to S is a function, then the image of f is the subset of S. F of capital R is the set of S and S such that there exists an R in R such that S is equal to f of R. So this is the collection of all images in the codomain of the function f. So we can also write it as the set of images f of R as R ranges over all the elements in R. Now note that f is surjective if and only if the image f of R is equal to S. And we have a corollary to the theorem. Corollary 3.11 tells us that if f from R to S is a ring homomorphism, then the image of f is a subring of S. And so to prove this, let's suppose that f from R to S is a ring homomorphism, and we need to show that the image of f of r, is a subring of S. And to show this, by theorem 3.6, we can show that f of r is non-empty and satisfies the properties SR1, which is closure under subtraction, and SR2, closure under multiplication. Now first note that by theorem 3.10, f of 0 sub r is equal to 0 sub s. So f maps the additive identity for r into the additive identity for s. And this implies that 0 sub s is the image of an element in r, so that means that it belongs to the image f of r. And therefore f of r is non-empty. Next we need to verify SR1, closure under subtraction. And so this says for all s and t in f of r, s minus t is in f of r. And so to prove this, we'll suppose that s and t are arbitrary elements of the image f of r, and we need to show that s minus t is in f of r. To show this, we need to show there exists an element r in capital R such that s minus t is equal to f of r. So we need to find an r and then verify that r satisfies our domain, namely it belongs to r, and our propositional function that s minus t is equal to f of r. Now, since s belongs to f of r, since s is in the image, then there exists an element u in r such that s is equal to f of u. And since t is in f of r, then there exists an element v in r such that t is equal to f of v. So we're going to choose r, the element we're looking for, to be u minus v. And since u and v are both in r, then r equal u minus v is in r. And the propositional function holds since f of r will be equal to f of u minus v, which is equal to f of u minus f of v. That follows from our theorem that f preserves subtraction, and this is s minus t. And so this proves the existential statement, and therefore s minus t is in f of r, and this shows that f of r is closed under subtraction. Now the proof of SR2 will be similar, and so thus f of r is a subring of S. Next we want to discuss existence of isomorphisms. So the properties of homomorphisms in theorem 3.10 can be used to help find an isomorphism between two rings or to show that no isomorphism can exist. So we'll start with an example. We want to show that Z12 is isomorphic to Z3 cross Z4. So Z12 is the set of integers, or the ring of integers, mod 12. And Z3 cross Z4, this is the Cartesian product of Z3 with Z4. So this is ordered pairs where the first element of the pair is from Z3 and the second element of the pair is from Z4. And we do our addition and multiplication component-wise within the respective rings. So to show that Z12 is isomorphic to Z3 cross Z4, we need to find an isomorphism mapping Z12 to Z3 cross Z4. Now by theorem 3.10, a homomorphism F from Z12 to Z3 cross Z4 must map the additive identity of Z12 to the additive identity of Z3 cross Z4, and the multiplicative identity of Z12 to the multiplicative identity of Z3 cross Z4. And this implies that f of 0 will be equal to 0, 0, and f of 1 will be equal to 1, 1. So the additive identity of Z12 is just 0, and the additive identity of Z3 cross Z4 will be 0, 0. The multiplicative identity of Z12 is 1, and the multiplicative identity of Z3 cross Z4 will be 1, 1. Now, using RH1, the preservation of addition property, we can then determine the images of the remaining elements of Z12. For instance, f of 2, this is equal to f of 1 plus 1, which is equal to f of 1 plus f of 1 using the preservation of addition property. And f of 1 is 1, 1, so this will be 1, 1 plus 1, 1, which is equal to 2, 2. So f of 2 is the ordered pair 2, 2. Then f of 3 will be f of 2 plus 1, which is f of 2 plus f of 1, which will be equal to 2, 2 plus 1, 1, which will be equal to 3, 3, but our first component's coordinates are mod 3, so this will be the ordered pair 0, 3. And then f of 4 will be f of 3 plus 1, which is f of 3 plus f of 1, which will be the ordered pair 0, 3 plus the ordered pair 1, 1, which will be 1, 4, but the second coordinate is mod 4, so this will be the ordered pair 1, 0. Continuing, we can obtain the images of all the elements of Z12. So f of 1 is 1, 1, f of 2 is 2, 2, f of 3 is 0, 3, f of 4, 1, 0, f of 5 is 2, 1, f of 6 is 0, 2, f of 7 is 1, 3, f of 8 is 2, 0, f of 9 is 0, 1, f of 10 is 1, 2, f of 11 is 2, 3, and f of 0 will be 0, 0. And this defines a bijection from Z12 to Z3 cross Z4. To show this is an isomorphism, we need to verify RH1 and RH2. We need to show that it's a homomorphism. Now we could do this by exhaustion, but that would obviously involve a lot of work. Instead, we can try to determine a formula for f. So let's let A sub 12 denote the congruence class of A in Z12. And A sub 3 will be the congruence class of A in Z3, and A sub 4 will be the class of A in Z4. It can then be shown that f is given by the formula f of the congruence class A sub 12 will be the ordered pair containing the congruence class A sub 3, comma, A sub 4 for each congruence class A sub 12 in Z12. For instance, using the formula, we obtain f of 7 sub 12 is equal to 7 sub 3, comma, 7 sub 4, and this is equal to 1 sub 3 and 3 sub 4. So the first coordinates are mod 3, the second coordinates are mod 4. And this matches what we stated earlier, that f of 7 is equal to the ordered pair 1, 3. We can now use this formula to verify RH1 and RH2. So to verify RH1, the preservation of addition, let's suppose that A and B in Z12 are arbitrary congruence classes, and we need to show that f of A plus B is equal to f of A plus f of B. So using the definition of f and the definitions of addition in each of our rings, Z12, Z3, Z4, and Z3 cross Z4, we obtain f of the class of A in Z12 plus the class of B in Z12 is equal to f of the class of A plus B in Z12. That follows from the definition of addition in Z12. And this is equal to the ordered pair containing the class of A plus B in Z3, comma, the class of A plus B in Z4. That's by the definition of f. And this will be equal to the ordered pair with the class of A in Z3 plus the class of B in Z3, comma, the class of A in Z4 plus the class of B in Z4. That follows from the definition of addition in Z3 for the first coordinates and in Z4 for the second coordinates. And this will be equal to the ordered pair class of A in Z3, comma, class of B in Z3. No, that's a mistake. That should be the class of A in Z3 and then the class of A in Z4 plus the class of B in Z3 and the class of B in Z4. And that follows from the addition in Z3 cross Z4. And so this will be equal to f of the class of A in Z12 plus f of the class of B in Z12. Okay, so in the next to the last, that follows from the definition of f. So in the next to the last line there, the first ordered pair should be A, class of A in Z3, class of A in Z4. And then the second ordered pair should be the class of B in Z3, class of B in Z4. And so with that correction, this shows that F satisfies RH1, and a similar proof will show that F satisfies RH2, and therefore F is an isomorphism, and hence Z12 is isomorphic to Z3 cross Z4. For another example, let's show that the rings Z4 and Z2 cross Z2 are not isomorphic. So Z4 is the set of integers, or the ring of integers mod 4, so that contains 0, 1, 2, and 3. And Z2 cross Z2 is the Cartesian product of Z2 with itself, so this will be the ordered pairs where each element comes from Z2. Each coordinate comes from Z2. And to show this, we'll use a proof by contradiction. So we want to show that the rings are not isomorphic, so let's suppose that they are isomorphic. So suppose Z4 is isomorphic to Z2 cross Z2. We then need to derive a contradiction. Since Z4 is isomorphic to Z2 cross Z2, then there exists an isomorphism F from Z4 to Z2 cross Z2. As in the preceding example, F must map the additive and multiplicative identities of Z4 to the additive and multiplicative identities, respectively, of Z2 cross Z2. So that tells us that F of 0 must be equal to the ordered pair 0, 0, and F of 1 must be the ordered pair 1, 1. Now, since F must preserve addition, since it's a homomorphism, then F of 2 will be equal to F of 1 plus 1, which is equal to F of 1 plus F of 1, which is the ordered pair 1, 1 plus the ordered pair 1, 1, which will be equal to the ordered pair 0, 0. So then we have 0 is not equal to 2, but F of 0 is the ordered pair 0, 0, and F of 2 is also equal to the ordered pair 0, 0. This contradicts the fact that F is injective. So 0 is not equal to 2, but F of 0 is equal to F of 2. And thus Z4 is not isomorphic to Z2 cross Z2. For another example, we can show that Z is not isomorphic to any of Q, the field of rational numbers, R, the field of real numbers, or C, the field of complex numbers. And to show this, we'll use a proof by contradiction. So let's suppose, for instance, that Z is isomorphic to Q, the field of rational numbers. We then need to derive a contradiction. Now, since Z is isomorphic to Q, then there exists an isomorphism F from Q to Z. And theorem 3.10 part 5 implies that F maps units in Q to units in Z. So part 5 of the theorem tells us that F preserves units. So that tells us that we know that every non-zero element in Q is a unit, since Q is a field. So this result implies that Z has infinitely many units. This is a contradiction, however, since Z only has 2 units, namely -1 and 1. And therefore Z is not isomorphic to Q. And an identical proof shows that Z is not isomorphic to either R or C. Now, since a ring isomorphism preserves addition and multiplication, an isomorphism also preserves any property that is defined in terms of the addition or multiplication. For example, we can show that commutativity is preserved under isomorphism. And this means for all rings R and S, if R is isomorphic to S and R is commutative, then S is also commutative. And to prove this, well, let's suppose that R and S are arbitrary rings. Suppose R is isomorphic to S and R is commutative. We then need to show that S is also commutative. To show this, we need to show for all S and T in S, S times T is equal to T times S. So let's suppose that S and T are arbitrary elements of S. We need to show that S times T is equal to T times S. Now, since R is isomorphic to S, then there exists an isomorphism F from R to S. And since F is surjective, then there exist elements R and U in R such that F of R is equal to S and F of U is equal to T. Then S times T will be equal to f of R times f of U, which is equal to f of RU. That's by property RH2, the preservation of multiplication. And this is equal to f of UR, since R is commutative, and U and R are both elements of R. And this is equal to f of U times f of R, that's by RH2 again, and this is equal to T times S. So therefore S is commutative.